Okay.
Assalamualaikum and good day everyone. My name is Madam Fadiatul Hasinah binti Muhammad. I'm going to discuss chapter 24, which is topic wave optics. For subunit of chapter 24, we have 24.1 condition for interference, 24.2 young double slit experiment, 24.4 interference in thin films, 24.6 diffraction, and 24.7 single slit diffraction. So for today, I'm going to discuss 24.1 and 24.2. At the end of this session, students should be able to: number 1, define coherent and incoherent light. Number 2, apply the condition for constructive and destructive interference to a young experiment. There are two conditions for interference happen. First is the light source are monochromatic, meaning that all the light has the same wavelength. And number 2, the source are coherent, which means that the wave they emit must maintain a constant phase with respect to each other. If this is true, interference will be constructive, where the two waves are in phase, and destructive, where they are out of phase. Okay, this is example of the wave that are in phase. Wave 1 and wave 2 have zero phase difference, or in phase, adding together and give the larger amplitude. So this is the larger amplitude. This is we call as constructive interference. However, for the wave that are half a wavelength, out of phase will interfere destructively. If the individual wave have equal amplitude, their sum will have zero amplitude. Notice that a 180 degrees difference in phase corresponds to the wave being out of step by half a wavelength. So this is the half of the wavelength. When waves are one wavelength out of phase, the result is again constructive interference, exactly the same as the wave are in phase. Okay, if the phase difference between the two waves is 360 degree, which corresponds to one full wavelength, 1 lambda. Okay, now we look at the concept test for wave A and wave B. If wave A and wave B are superposed, meaning that their amplitudes are added, the resultant wave is either number 1, 2, 3, or 4. So what's the answer? The answer will be number 3. So the amplitude of wave A and wave B have to be added at each point. Okay, now we proceed to the 24.2 Young double slit experiment. Thomas Young first demonstrated interference in light wave from two sources in year 1801. Light is incident on the screen with a narrow slit S0. Please refer to this figure. So this is the S0. The light wave emerging from this slit arrive at the second screen that contains two narrow parallel slits S1 and S2. The narrow slit S1 and S2 act as source of wave. The wave emerging from the slit originate from the same wave front and therefore always in phase. Okay, the light from the two slits form a visible pattern on a screen. Imagine that this is your screen. The pattern consists of series of bright and dark parallel bands called fringes. So this is your bright fringe. Constructive interference occurs where a bright fringe appears, while destructive interference results in the dark fringe. Okay, there are a few interference patterns. Now we look at for interference pattern number 1. Two waves which leave the two slits in phase, means slit 1 and slit 2, strike the screen at the central point P here. Because these waves travel equal distance, so they arrive in phase at point P. As a result, constructive interference occurs and a bright fringe is observed at point P. Okay, for interference pattern number 2, the upper wave has to travel farther than the lower wave. So, means that the upper wave is from the slit 1. Okay, the upper wave travel one wavelength farther compared to lower wave. Therefore, the wave arrives in phase at point Q. When the path length differ by a wavelength, the waves are in phase and undergo constructive interference at point Q. So, a bright fringe occurs at point Q. For interference pattern number 3, the upper wave travel one half of the wavelength farther than the lower wave. But we can see from the figure here, the throw of the bottom wave overlap with the crest of the upper wave, giving rise to destructive interference. As a result, a dark fringe is observed at point R. As a conclusion for the interference pattern, interference will be constructive where the path length differ by n integral numbers of wavelength, while the destructive happen where they differ by a half odd integral numbers of wavelengths. Okay, now we can calculate the geometry of Young double slit experiment with the help of these figures. Consider a point P on the screen where the screen position distance L from the slit S1 and S2, which are separated by the distance of D. The R1 and R2 are the distance of the wave travel from slit 1 and slit 2 to the screen. So, we assume that wave emerging from slit 1 and slit 2 have the same constant frequency and have the same amplitude. The light intensity at point P is the result of the light from both slits. What we can see here, a wave from lower slit, however, travel farther than a wave from the upper slit, which is slit 1, by amount of d sine theta, meaning that the distance R2 minus R1 be called as the path difference or known as delta. Okay, so the equation for path difference delta equal to R2 minus R1 equal to d sine theta. Okay, now how we calculate or how we got the delta equal to d sine theta. So delta is the path difference between R2 and R1. So from this small triangle, theta here, sine theta equal to delta over d. So we got that delta equal to d sine theta. This assumes the paths are parallel, which is approximately true because L is much greater than D. For a bright fringe produced by constructive interference, the path difference delta must be either 0 or some integral multiple of wavelength like 1, 2, 3 and so forth. Therefore, the condition for constructive interference or bright fringe at point P is given by delta equal to d sine theta equal to m lambda, where m is the order number. For example, when m equal to 0, meaning that it is the 0th order maximum or central bright fringe. When m equal to 1 or plus minus 1, it is called the first order maximum on either side. When delta is an odd multiple of half lambda, the two waves arrive at point P are 180 degrees out of phase and giving rise to the destructive interference, meaning that a dark fringe is observed. This needs a path difference of an odd half wavelength. Therefore, the condition for dark fringe or destructive interference given by delta equal to d sine theta equal to m plus half lambda, where m can be 0, plus minus 1, plus minus 2 and so forth. For example, if m equal to 0, the path difference is delta equal to half lambda, which is the condition for the location of the first dark fringe on either side of the central bright maximum. If m equal to 1, the path difference is delta equal to 1.5 lambda, which is the condition for the second dark fringe on each side. It is useful to obtain the expression of position of the fringes that can be measured vertically from 0th order maximum. Let's say I put point O here. Y is the position of the fringes. Okay, according to this triangle, we have theta here. So tangent theta equal to y over L. So y equal to L tangent theta. With the assumption of L is much greater than D, and also we assume that D is much greater than lambda, this assumption can be valid because in practice L is often on the orders of 1 meter, D is a fraction of a millimeter, and lambda is a fraction of micrometer for visible light. Under this condition, theta is small, we can use the approximation sine theta equal to tangent theta. So, therefore, the equation of position y equal to L tangent theta can express in terms of y equal to L sine theta. Okay, this is the equation for position of bright fringe and dark fringe. So, how we get this equation of the position? So previous slide, we have the equation of y equal to L sine theta, right? So we also have the equation of d sine theta equal to m lambda. So we substitute sine theta equal to m lambda over d. In this equation, we have got the equation of position y equal to lambda L over d times m. And the position for dark fringe is y equal to lambda L over D times m plus half, where for both cases m equal to 0, plus minus 1, plus minus 2, and so forth. Okay class, now we have one example on the question of Young double slit experiment. Now let's do it together. A screen is separate from a double slit source by 1.2 meter. So this is your L. The distance between the two slits is 0.03 millimeter. So this is your D. The second order bright fringe M equal to 2 is measured to be 4.5 cm from the center line, meaning that this is your position Y. So question asks to find the wavelength of the light. Okay, you have the equation of y equal to lambda L m over d, right? In order to find the wavelength or lambda, you just rearrange this equation. So lambda equal to yd over ml. By substituting all the value here, you will get the lambda equal to 5.63 times to the power of minus 7 meter, or you can put as 563 nanometer, or 563 nanometer. But make sure every calculation here, the unit must be converted to the meter first. Alright, so I think that's all for today. Thank you for your attention. So have a nice day. Assalamualaikum.
Okay, so let me look at the slide. Okay, this is the slide. I will share the slide later. Okay, don't worry. Okay, so let's look at what we have learned just now about the wave optics, right? Okay, wait. Okay, can you see the slide?
Yes.
You. Okay, so let's look at what the madam had explained about the wave optics. So first of all, this is the units of chapter 24, which we will learn anything about interference, the Young double slit experiment, and also the interference in thin films, diffractions, and lastly the single slit diffractions. Okay, so based on the videos, she only explained about the conditions, or she only explained about the units of the chapter 24 for 24.1 and 24.3 and 24.2. Yeah, only based on these two things. Actually, in this chapter, okay, we will learn some things that related to interference. Before this, in your first semester, you already learned about sound, okay, sound interference. But today, I want to explain to you that not just interference on sound, okay, because sound is a kind of wave. So right now we are learning about light. Okay, light. So light acting as a wave, so therefore it will encounter interference. Okay, interference means, okay, a combinations. Another words for interference is a combinations of wave. Either is going to be constructive or destructive. Okay, so how can the wave, okay, encounter, when wave encounter, okay, let's say can try to imagine wave encounter one slit, what will happen, and wave, when wave encounter two slit, okay, what will happen. So one slit here is considered to be diffraction, while when wave encounter two slits, it will be based on the Young double slits. Okay, try to think. For single slit, okay, I will explain later. Okay, but right now I want to explain on the Young double slit experiment. That's why the words is the Young double slit experiment. Okay, because it involves two slits, dua celah. Okay, dua celah. So that's why we are learning about interference. Okay, so for the wave, sifat dia, the characteristics of wave is actually when it encounter a slit. Okay, bila dia melalui celah, apa yang berlaku ialah dia akan diffract. That's why you have to imagine this thing. Bila wave lalu slit, okay, so ada slit. So bila wave lalu, apa yang akan dia buat? Dia akan diffract. Dia akan berlaku pembelauan. Dulu ayat dalam bahasa Melayu dia pembelauan. Dia akan lebih besar. Especially when the wavelength is greater, is not is less than the slit. Less than the width of the slit tu. Okay, so dia akan jadi diffraction. Sebenarnya itu sifat dia. Dia akan jadi diffraction. Maksud dia akan jadi diffraction. But kalau dalam single slit, it will only occur diffractions. But what will happen kalau kita ada dua slit? So yang bawah ni pun akan ada interference juga. So bila dua-dua ni combine, ini yang satu, ini yang dua, dua-dua ini combine, terhasillah a dark and bright fringe. Ini screen. Okay, screen. So kita lah dapat menghasilkan dark and bright fringe. So itulah yang dinamakan interference. So ingat, wave bila di-combine, it becomes interference. Okay, but wave itself, when it encounters a slit, okay, dia lalu di celah, dia akan menghasilkan diffraction. Okay, so maksud dia dalam ni pun adalah diffraction. Okay, dalam ni pun ada diffraction. Tetapi bila dua-dua diffraction berlaku, terhasillah interference. So I want to get the highlight first of the chapter, because you need to know, okay, why you learning this. Okay, because you want to learn, or you want to explore how the wave combine when we have two slits or single slit. Okay, so we learn about double slit first. So the double slit, two diffraction involved. So when two diffraction involved, so when it combine, it becomes interference. Very easy to understand. Okay. So at the end of the session, okay, the student should be able to define coherent and incoherent light. So this okay. So this is the conditions for interference. Okay, the conditions for interference. So interference is only noticeable if the light sources are monochromatic. It's very good to understand the monochromatic. Okay, what is monochromatic? Has the same wavelength. Same wavelength. Okay, so all the light source must be monochromatic. Okay, untuk nak buat interference, remember you must have two slits. Ada dua slit. So kalau kita ada lampu suluh dekat sini, ada lampu suluh, tak boleh letak lampu suluh yang nombor 2, tak boleh. Okay, you cannot put another torchlight over here. You must use the only single torchlight, because we can only obtain a wavelength from the same torchlight. Not same type, but on the one torchlight only. Sebab tu we need to get the light sources must be monochromatic. And number 2, the light must be coherent. What is coherent? Different source maintain the same phase relationship. Okay, maintain the same phase relationship. Okay, so in the interference, okay, you will have a constructive and destructive. Okay, you dah belajar dah benda ni. What is constructive, what is destructive, kan? No problem. Okay, this is considered to be constructive when you have a zero phase difference. Yeah, look at the word zero phase different. Apa maksud zero phase different? Okay, look at the point here. Can you see? This is the point. Let's say this is point A, and this is the point A prime. And all the time, point A and point A prime, let's say I put another value. I put another point. Yeah, I put another point here. Let's say B prime and also B. All are on the same phase. As zero, as no difference between graphs of sinusoidal number 1 and also graph of the sinusoidal number 2. There are no different. Look at how they put the point A and point A prime. Okay, you can see all the points are parallel to each other. Okay, not exact or parallel, but it's on the form. Okay, let's look at graph number 1. Okay, point A is at the peak of the graph, and so that so to be the A prime. A prime also at the peak, okay, at the maximum value. So when this occur, it will have a constructive interference. Very easy to understand. But the correct term is the zero phase difference. Okay, zero phase difference. Okay, so this is the wave that has half a wavelength out of phase. Okay, look at the word half a wavelength out of phase. Okay, definitely out of phase. When out of phase, okay, look. Okay, definitely. Okay, if you put A and A prime are not on the same phase. Okay, as usual, this is A at the peak of the graph, and A prime is at the peak of the graph, but in the negative value. So that's why we are saying that the peak is not the same. So we cannot say that this is in phase. Okay, the graph are in phase. No. Okay, so that's why we are saying that the wave is actually at the half a wavelength out of phase. So when this occur, it will uh, you will get a destructive interference. Okay, so destructive interference. Look at how it happens that then all the possible wave will be the decline. Okay. So when one wavelength, one wavelength uh, out of phase, okay, the result is again a constructive interference. Okay, this is how it gets one wavelength out of phase. So we are saying now is okay that this is A prime, this is point A, okay, for the graph number 1, and for the graph number 2, the A prime will be one wavelength away, okay, one wavelength out of phase. This is another one, meaning that okay, the graph started at the graph number 2 started earlier, one wavelength earlier compared to graph number 1. Okay, so meaning that A prime is one wavelength, okay, of should I say one wavelength different between A prime and also A. So that when we have one wavelength, okay, so first for constructive, so zero wavelength is zero phase difference, one wavelength, yeah, and then we can also predict that for two wavelength, three wavelength, and so on, okay, the numbers will give you constructive interference. But for destructive interference, okay, normally it involve the 0.5 lambda, okay, 1.5 lambda, 2.5 lambda, and so on. Okay, when we don't have an integer number, so yeah, it will be the destructive. Okay, this is the concept, right? So this is the Young double slit experiment, okay, demonstrated by the in 1801 by Thomas Young. Okay, so he used the same. Look at the screen here. Okay, first of all, how can he get okay, the possibility of double slit experiment, okay, a series of dark and bright fringe, okay, on the screen itself. Okay, how can he get it? Okay, first of all, he will have the same source. Okay, maybe, okay, he will have a monochromatic source. Okay, a monochromatic source coming here as a wavefront, and first of all, it encounters first a single slit. Single slit dulu. Dia akan lalu dekat single slit dahulu. Di sini ada satu slit saja. Okay, apa yang berlaku dekat sini? The wave will be diffract, akan berlaku pembelauan. Kenapa dia nak buat macam tu? Sebab dia nak besarkan lagi wave yang kita ada. Okay? Dia nak besarkan lagi, dia nak serakkan lagi, okay? Pembelauan, dia nak belaukan lagi wave tersebut supaya, okay, when it encounter a double slit, so this is where he get the double slit here. Nampak dekat sini ada S1, S2. S0 is considered to be single slit. So, this is double slit. And then, afterwards, apa yang berlaku? Dekat S1 berlaku diffraction. Dekat S2 pun berlaku diffraction. Okay, the diffraction occurs at S1 and S2. And afterwards, this is where you get the interference. Kalau orang tanya, where is the interference? Here. When you put the double slit. At the single slit, does it interference? No. Okay. At the single slit, it only have diffraction. Dekat sini berlaku diffractions only. Single slit. And apa tujuan dia lalu dekat double slit? Dia nak besarkan. Dia lalu kat double slit, dia nak bagi wave itu combine. Okay, combine dan menghasilkan a series of dark and bright fringe. You can see that, okay, here is the maximum. Okay, maximum here considered to be zero path different. So every time you see maximum, that will be the bright fringe. In our term, that will be the bright fringe. So this is bright fringe number 1. Then bright fringe number 2. This is bright fringe for -1 and also -2. However, in between the maximum, of course, from 0 to 1, you will obtain 0.5. So this is 0.5. This is 1.5. This is -0.5. This is -1.5. Okay, so in between bright fringe, there will be a dark fringe. So the dark fringe occurs when you have a destructive interference. Bright fringe for constructive interference. Okay, so need to understand on this part. Okay, all right. So this is where they put in a lot of so this is incoming light that is considered to be monochromatic. Okay. Use the word terms, monochromatic, and then it will be diffracted, okay, and then encounters a double slit. Okay, encounter double slit, and then you can see a series of dark and bright fringe. Okay, can you imagine it? So please, okay, so this is considered to be your screen. This is your screen. Okay, that will be your screen. Okay, so the light from the two slits from a visible pattern on screen. The pattern consists of series of bright and dark fringe. Okay, so this is the interference pattern number 1. Okay, look at how they behave. Okay, this is actually it is come from, okay, both wave coming from the double slit. Okay, consider maksudnya dekat belakang ni adalah single slit, okay, dengan light source coming from here. So tapi dia tak lukis, dia terus lukis dekat double slit ni. Okay, when you have two slits of S1 and S2, so these slits, okay, to a point P, where at point P, apa yang berlaku dekat sini, okay, the upper wave, here, okay, two wave travels the same distance. So bayangkan ya, at S1, the wave will travel let's say 10 meters. And at point 2, the wave is also travel 10 meters. Okay, so we are saying wave travel from both this pattern as from slit number 1 and slit number 2 at 10 meters uh, respectively. Okay, so we are saying that they, okay, as a result, they arrive in phase. What happened when the wave are in phase? We are saying that this is a constructive interference. Okay, so meaning that when 10 meters minus 10 meters, it become 0. This 0 meters considered to be 0 path length different. 0 path length difference, which means 0 lambda. At 0 lambda, you will see because of the two waves travel at the same distance. So look at the pattern number 2. Okay, pattern number 2, okay, okay, the upper wave has to travel farther than the lower wave. Okay, maksudnya wave yang travel daripada S1 will be akan lebih 1 berbanding S2. Okay, contoh dia, if S2 is travelling at 9 meters, so wave from S1 will travel 10 meters. Dia akan lebih 1. So bila kita tolak 10 minus 9, you will get 1 meters. Okay, you will get 1 meters. Therefore, the wave once again arrive in phase. So you can see a bright fringe occurs. Okay, this series of bright fringe. Okay, so bila faham lah, bila bright fringe, then this is the constructive interference. Okay, as I mentioned to you, okay, for constructive interference, normally it will start at 0 lambda, 1 lambda, 2 lambda, 3 lambda, and so on. At least the number must be integer number. Okay, integer without decimal. If the decimal number occurs, then it will lead to the dark fringe. Okay, so this is pattern 3. So the upper wave travels 1/2. Okay, 1/2 of a wavelength farther than the lower wave. So contoh dia, kalau 1/2 ni 0.5 ataupun 1.5 lah kan. Okay, kita boleh anggap 1/2 is 0.5. Okay, so let's say this one is 10.5 and this one is 9. So you will get 1.5. Okay, so kalau dekat sini 10, kita akan dapat different dia 0.5. Doesn't matter, but it still have a 1.5 different. Okay, further. Therefore, at point R, you will get destructive interference. Okay, and by looking at the screen, you will see a dark fringe. So the dark fringe is for destructive interference, that for the interference. Alright, so in this illustration, interference will be a constructive where the path length different by an integral number of wavelength, integer, and destructive where they differ by a half odd integral number. Okay, so this is the geometry of the Young double slit experiment. Okay, Young double slit experiment. So, okay, that one, before this, we learned about the path length difference, the difference. Okay, so this is where you want to calculate. You want to do it in a very numerical analysis. You want to do it in a very good. You want to analyze the Young double slit experiment in a numerical number. So we need to use this geometrical of a Young double slit experiment. Okay, so let's look at this example. So when you now, okay, you should consider, okay, the slits have a different, okay, the slits is have a different or dipisahkan dengan D. Ini antara benda-benda yang penting ya. D is the small letter d is the difference measurement on different length of S1 and S2, between S1 and S2. Okay, another one is the L. L is the length from the label slit to the screen. Okay, that is number one. And number two is theta. Theta here. Okay, you can see that in this kind of you can look at the yellow triangle. Look at this part. Okay, at the yellow triangle. So this is considered to be wave from S1, and S2 R2 will be wave from S2. Okay, okay. As I said to you before this, okay, R1 and R2 will travel a different distance. Okay. For example, R1 is considered to be 10 meters, while R2 to be 12 meters. But that is, we know, okay, when 12 minus 10, 12 minus 10, you will get 2 meters. So we know. So how to do it? So this is the delta. Okay, this is the delta, or should we call that as the path difference between the two rays. So at 12, okay, try to imagine 12. 12 is based on what? It's based on 10 plus 2. Remember, 10 plus 2. So 10 is the one from R1. 10 tu sama panjang, which is dekat sini sebenarnya 10 je. Dekat sini 10 sama 10 panjang, tapi lebihan dia ni ialah 2. So yang tu itulah dipanggil the path length difference. So how to get it? So R2 minus R1 equivalent to d sine theta. How can they get the d sine theta? From the simple trigonometry function. So this is the theta. So this should be the d should be the hypotenuse. Okay, this should be the hypotenuse. So the theta will be, so the difference here is the delta is equivalent to sine d sine theta. Okay, d sine theta. Or should we get it as okay, delta over d? Okay, delta over d is equivalent to sine theta. So you get delta over d. This is not the distance. D is not the distance. Delta is not the distance. Delta is the different. Okay, delta to different. Is equivalent to sine theta. So delta is equivalent to d sine theta. So what is delta? Delta is R2 minus R1, or the difference between the path length traversed by the rays. Okay. This assume the paths are parallel. So this is why I give my explanation. Okay. So for bright fringe produced by a constructive interference, the path difference must be either 0 or some integral multiple of the wavelength. So from here right now, okay, we can obtain that the d sine theta is equivalent to m lambda for the bright fringe. Okay, so for the bright fringe. So m is called the order number. Remember, this order number start at the 0, because 0 phase different, 0 path different is also considered to be bright fringe. Okay, bright fringe. Okay, they start at 0 and so on. 0, number 1, 2, 3, and so on. -1, don't forget, we also have the below part, the -1, -2, so that's why you can see this is have +1 and -1, positive and -1, positive and -2, positive and -3, and so on until infinity. Okay, so m is called the order number. When m is plus and minus 1, it is called the first order maximum. Okay, a lot of terms that will be used inside the question. For example, maximum is also considered to be bright fringe, and of course the bright fringe itu menunjukkan constructive interference. Ada lagi beberapa terms yang digunakan. Okay, but as we encounter the questions, then we know. Okay, maximum, bright, dia boleh bagi tahu pasal constructive interference. So that is all d sine theta equals to m lambda. Okay, so for the destructive interference, a dark fringe is observed. Okay, and this needs a path difference of an odd half wavelength. Odd half wavelength. Okay, so m is the order number is still 0 plus minus 1 plus minus 2, but in the equation itself they put positive half, positive 1 over 2. Okay, look at how they get it. Okay, if the question asks you the second dark fringe, a second dark fringe, okay, if before this, let's say the first dark fringe, the first bright fringe, so you can put m equals to 1 or m equals to negative 1. But if the question asks you about a zeroth law, so you can put 0. If the question asks you about the 10 bright fringe, so you can put 10 at m. Okay, but so with the use of this kind of equation, which means d sine theta equals to m plus half lambda. Remember, okay, how to put m, the correct m. So if m equals to 0, a path difference is delta equals to lambda over 2. Okay, lambda over 2. Why? Because it's when m 0, so 0 plus 1 over 2 become 1 over 2 lambda. So 1 over 2 lambda is lambda over 2, which is the conditions of the locations of the first dark fringe. So of the first dark fringe. Okay, so first dark fringe m equals to 0, the second dark fringe m equals to 1. So you need to minus 1. So when the question asks you about the first dark fringe, okay, the first dark fringe, then you put m equals to 0. And for second dark fringe, okay, if the question asks you about the second dark fringe, then you know that you should put m equals to 1. Okay, you must minus 1 first. The second means 2, right? 2 minus 1, so the m equals to 1. How about 1? 1 minus 1, then m equals to 0. If they give you a 10 dark fringe, okay, for example, 10 dark fringe, okay, what is the value of m? They should put as f 10 equals to m equals to 9. Okay, 9 plus half, so you become 9.5 lambda. Okay, so try to do it, okay, as a basis. Right, and this is the positions of the fringes that can be measured vertically from the 0 order maximum. Okay, so instead of using the path difference, which is d sine theta equals to m lambda, or d sine theta equals to m plus half lambda, right? Now you will have another equations to help you in order to get or to at least to be used inside the interference double slit experiment. So the position of the fringes can be measured vertically. All right. So in these terms, the L is still L. Now you will only have one theta instead of d sine theta. Okay, so we don't bother about the, and then you will have y. Okay, so definitely tangent theta is equivalent to, this is the triangle, y over L. Okay, y over L. So y is equivalent to L tangent theta. Okay, L tangent theta. So what is y? Y is the should we call it as a position? Okay, positions from the 0 order maximum. The 0 order maximum is at when the 0 path length difference. So when 10 minus 10 equals to 0, so it starts from here until where we want to calculate. So this is y. So y is the position, jarak daripada mana? 0 order maximum, daripada kosong sampai ke berapa-berapa lah, tak kisah, because they only want to calculate the position. Okay, so the assumption now is the L will be much more bigger compared to D. So that's why now we can left that D becomes D sine theta, and lambda is equivalent to lambda. D is equivalent to lambda, and therefore, okay, you will see that for the bright fringe, you will have this kind of equations. Okay, because y equals to L tangent theta, and theta is very small, therefore you will have L sine theta. And remember before this that d sine theta equals to m lambda, so sine theta equals to m lambda over d, so you get this thing into here. So that's why you can get L m lambda over d. Okay, and L lambda over d. Right? So you can also use this one. Okay, when you encounter a position, okay, when the words they want to see the positions. Before this, the questions only involve d sine theta. Maybe want to calculate the lambda, or maybe wants to calculate the theta, or maybe wants to calculate the difference between the slits. Okay, but not the position. So when you be asked to calculate the position, you need to use this equation, or you can combine this equation by the assume that the tangent theta, okay, tangent theta is much more, the theta it will be equivalent to sine theta. Okay, so this is the assumption made by physicists. So this is the examples of a screen separated by a double slit by source. So okay, so a double slit source by, so this is considered to be D, the distance between two slits. Sorry, this one is the screen. Sorry, this one is L. The distance between the two slits, this one is D, and the second order bright fringe. So exactly M equals to 2. Okay, then you can put and determine the wavelength of the light. Wavelength of the light. So when the question doesn't give you theta, okay, there is no theta here. So you can easily get you, okay, don't use theta. So but you can use okay, measured to be 4.5. The second uh, order bright fringe is measured to be 4.5 centimeters. So 4.5 centimeters is y. Okay, because you cannot put d or whatever. So y equals to m l lambda over t. Okay, so what you want to calculate, you want to calculate lambda. Lambda is dy over ml, dy over ml, and definitely you will get some things that I don't remember the answer. If I'm not mistaken, 563 nanometers. All possible answers are all possible values. When you substitute, make sure it be in SI unit, which is meters. Okay, which means meters. Okay, so I think we'll stop here for a few minutes. So if you want to get some, okay, get some air, so please. Okay, we take a break for 1 or 2 minutes before we continue. Okay. Okay, so let's continue. Okay, so I will play some videos. So afterwards, then I will explain. Okay.
Assalamualaikum and good day to everyone. I am Puan Akmal Hidayah, and in today's lesson, I'm going to continue with the second part of wave optics. In today's lesson, we're going to look into what causes thin film interference, what is diffraction, and the interference pattern produced by a single slit and diffraction gratings. At the end of today's lesson, you should be able to describe thin film interference phenomenon qualitatively. You should be able to explain the diffraction pattern produced by a single slit. You should be able to apply the following formula to locate the first minima in the single slit diffraction pattern, as well as able to describe the condition for maxima in the interference pattern produced by diffraction grating. We're going to begin our discussion with thin film interference. Thin film interference is a natural phenomenon that happens in our everyday lives. For instance, you must have seen a rainbow-colored reflection in a pool of water on the road, like what you can see in the figure on the right, colorful pattern on a soap bubble. The brightest colors on the soap bubble are those that interfere constructively. This effect is what we call thin film interference. Thin film interference is a phenomenon that is a result of light wave being reflected off from different surfaces of a thin film. Thin film is defined as a layer of material ranging from fractions of a nanometer to several micrometers in thickness. Interference depends upon these factors: the thickness of the thin film, the refraction index of the material above and below the thin film, the index of refraction of the thin film, as well as the wavelength and angle of the incident light. To determine whether the reflected rays will interfere constructively or destructively, we must understand the following facts. When light travels through a medium with a smaller index of refraction towards a medium with a larger refractive index, it undergoes a 180-degree phase change upon reflection. 180-degree phase change is also equivalent to half lambda. Number two, when light travels from a larger index of refraction medium towards a smaller refractive index medium, there is no phase change upon reflection at the boundary. Number three, the wavelength that is important for thin film interference is the wavelength within the thin film, not the wavelength in the vacuum. Therefore, to calculate for the wavelength in the thin film, the following equation is applied. To refer to this particular equation, this component here is the wavelength of light in the thin film. This is the wavelength of light in vacuum, and n refers to refractive index of the thin film. What causes thin film interference? If you refer to the figure on the right, the blue colored layer in the middle is our thin film. You can see that the medium above and below the thin film is air. So we are now dealing with two different media. T in the figure refers to the thickness of the thin film. So this is how thin film interference takes place. When monochromatic light strikes the film, reflection occurs at the top surface of the film and produces the light wave represented by wave 1. This incident ray is only partially reflected from the top surface of the film. Refraction also occurs and causes the remainder of the light to enter the film. So this reflected ray will continue to travel through the thin film until it reaches the bottom boundary of the thin film, and once it reaches this particular boundary, it will once again be partially reflected and partially refracted. The partially reflected light will continue to travel through the thin film and re-emerge into the air to produce the second reflected ray. The second reflected ray will then combine with the first reflected ray to produce thin film interference. Take a look at the first reflected ray. The first reflected ray will experience 180-degree phase change upon reflection. This is because when this incident ray has reached this particular boundary, it is heading towards a medium with a higher index of refraction. That is why upon reflection, this reflected ray will experience 180-degree phase change. That is, if the one incident on this particular point is a crest, then the one reflected will be a trough. So 180-degree phase change is also equivalent to half lambda. As for the second reflected ray, it will not experience any phase change because it is being reflected off from a boundary that leads to a medium with a smaller index of refraction. So therefore, the second reflected ray will not experience any phase change. But it had to travel an extra distance of 2t before it can re-emerge into the air to combine with the first reflected ray. So therefore, in order to determine whether the two reflected rays will interfere constructively or destructively, we need to take into consideration the path difference between these two reflected rays as well as phase reversal or phase change. In general, in dealing with constructive interference in thin film, we will apply the first equation. The second equation is applied when we are dealing with destructive interference in thin films. These two equations are applied when we are dealing with two different media. If we are dealing with three different media, that is, you have a different medium above and below the thin film, then you have to reverse these two equations. That is, now the first equation becomes the equation for destructive interference, and the second equation becomes the equation for constructive interference. Once again, these conditions take into account two factors, that is the path difference between the two reflected rays, as well as the 180-degree phase change upon reflection. Example 1. Calculate the minimum thickness of a soap bubble film with a refractive index of 1.33 that will result in constructive interference in the reflected light if the film is illuminated by light with a wavelength of 602 nanometer in free space. What we need to do first is to determine the number of mediums that we are dealing with. If you read the question carefully, we have soap bubble as our thin film. So that means we have a soap bubble as well as air. So we have two different mediums. Since we are dealing with two different medias, that means we have to apply the first equation. That is for constructive interference. We have 2nt equals to m plus half lambda. We substitute all the information and we'll take 0. Our lambda is 602 nanometer. Refractive index is 1.33. From here, we get to calculate for the minimum thickness of the thin film as 113 nanometer. Next question. We calculate the minimum thickness for constructive interference when the soap bubble film is on top of a glass slide with a refractive index of 1.5. Okay. If you read the question carefully, now your thin film is on top of a glass slide. So in total, we have 3 different medias. That is, we have air, soap bubble as our thin film, as well as glass. So this is the situation for question B. We are now dealing with 3 different medias. This is the first medium, second medium, and third medium. So this is the refractive index for the first medium. Second medium is our thin film, and this is the refractive index for the third medium. From here, when this incident ray reaches the upper boundary of the thin film, upon reflection, the reflected ray will experience 180-degree phase change because this particular incident ray is heading towards the medium with a higher index of refraction. Okay, next, when this incident ray reaches the bottom or the second boundary of the thin film, it will also experience 180-degree phase change because the third medium has a bigger index of refraction. Okay, so the second refracted ray will experience 180-degree phase change as well as an additional path length of 2t. Okay, so now that we know we are dealing with constructive interference involving 3 different medias, therefore we have to reverse the 2 equations. Now the first equation becomes the equation for destructive, and the second equation becomes the equation for constructive. So we are now going to apply this particular equation. You can get all the information from the question, put in all the information, and from here, the minimum thickness of the thin film is calculated at 126 nanometer. Diffraction. Definition of diffraction: change in the directions and intensities of a group of waves after passing by an obstacle or through an aperture whose size is approximately the same as the wavelength of the wave. In other words, the light bends from a straight line path and enters the region that would otherwise be shadowed. This spreading out of light from its initial line of travel is what we call diffraction. In general, diffraction occurs when a wave passes through small openings around obstacles or by sharp edges. Basically, light must first be diffracted before it can overlap or interfere with one another to produce interference pattern. In figure A, if light did not spread out after passing through the slits, no interference would occur because they could not overlap or interfere with one another. In figure B, the light from the 2 slits overlaps as it spreads out, filling the expected shadowed regions with light and producing interference fringes. That is why the light waves must be diffracted. Once they are diffracted, they are able to overlap and interfere with one another to produce a series of bright and dark spots. This is an example of interference pattern produced by a single slit. You can see at the center of the pattern is a bright spot with a maximum intensity. Single slit diffraction. Once again, diffraction refers to the bending of wave that occurs when a wave passes through a single narrow opening. When a monochromatic coherent light falls upon a small single slit, it will produce a pattern of bright and dark fringes. The analysis of the resulting refraction pattern from a single slit is similar to what we did for the double slit. This one you have done in the first part of wave optics when you learn on Young's double slit experiment. This is a figure of the interference pattern produced by a single slit. So this particular screen is a screen with a single slit. A refers to the width of the slit. The second screen is the viewing screen where you will be able to see the interference pattern produced by the single slit. L is the distance between the two screens. At the center of the interference pattern is always a bright spot with maximum intensity. So Y1 refers to the position of the first minima on both sides of the interference pattern. Y2 refers to the position of the second minima on both sides of the interference pattern. Now, when it comes to the interference pattern, it is symmetrical. So if you were to fold the pattern to 2, we're getting the same size. So once again, it is symmetrical. For single slit diffraction, the light intensity is a maximum at the center of the screen. So this one is called 0th order maximum, and it decreases to a minimum at the angle given by the following equation. So in single slit interference pattern, this particular equation is applied to determine or to locate the position of the dark spots. If you compare this equation to the equation in double slit, the same equation is applied to locate or to determine the position of bright spots in double slit. So in single slit, this equation is once again applied to locate the position of dark spots. And in the equation, refers to fringe order number, it begins with 1 because 0 over here is a bright spot. Lambda is wavelength of light and A refers to width of the slit. These two quantities are measured in meter. You can also see that the width of the central bright maximum extends from the first minima on one side up to the first minima on the other side. So if you want to calculate for the width of the central bright maxima, you just need to calculate for the distance from the midpoint of the central bright fringe up to the first minima. And then once you have calculated for the vertical length over here, you just need to multiply your answer by 2. That will give you the magnitude of the width of the central bright maxima. Once again, although the equation for constructive interference in double slit has the same form as the equation for destructive interference in single slit, they have different meaning. The first case describes the bright regions in a two-slit interference pattern, and the second case describes the dark regions in a single slit interference pattern. Second example. Light passes through a slit and shines on a flat screen located 0.4 meters away. The wavelength of the light is 410 nanometer. Distance between the midpoint of the central bright fringe and the first dark fringe is 1. Determine the width of the central bright fringe when the width of the slit is 5 negative 6 meter and 2.5 negative 6 meter. Okay. So now you are going to apply this particular equation to locate the position of the first minimum. We have sine theta equals to m lambda over A. The order number of fringe number is 1. This is the wavelength of the light. A refers to the width of the slit. From here, you get to calculate for the angular position of 4.7 degrees. If I go back to the previous slide, the 4.7 degrees is over here. So that is the angular position. But you are not calculating for angular position. What you want is the vertical position. So from here, we're going to apply for tan function. So it's tan theta equals to y over L, opposite over adjacent. So it's tan 4.7 degree equals to the vertical position over 0.4. From here, you get to calculate for the vertical position of the first minima measured from the midpoint of the central crack range, that is 0.032886 meter. But like what I have mentioned earlier, the width of the central bright maxima extends from the first minima on one side up to the first minima on the opposite side. So what you do from here, once you have calculated for the vertical position, you can simply multiply your answer with 2. So that will then give you the width of the central bright maxima is equal to 0.066 meter. Next, you can try the second equation. You can try the second question with the same procedure. So this is the suggested answer, which is 0.13 meter. Next is example 3. Light of wavelength 750 nanometer passes through a slit 1 times 10 negative 3 millimeter wide. How wide is the central maximum in degrees and centimeters on screen located 20 centimeters away? So what we do, we're going to apply this equation, calculate for the angular position of the first minima. We substitute all the values. This is 1, this is the wavelength, this is the width of the slit, and that will give us an angular position of 49 degree. But 49 degree is only this part. You want the width of the central bright maxima. So what you do is you multiply your answer by 2, and that will give you 98 degree. 98 degree. So 98 degree is the width of the central bright maxima in degree. Next, you want to convert your answer to centimeter. So what you do, from the angular position, you're going to apply your tan function. So it's tan 49 degree equals to x over 20 centimeter. Once you've calculated for this vertical position, you multiply your answer by 2. That will then give you the width of the central maximum in centimeter. That is 46 centimeter. You can try and do example 4 on your own. I've also provided the solution and answer for example 4. The diffraction grating. Diffraction grating is an optical device used to learn the different wavelengths or colors contained in a beam of light. Diffraction grating consists of a large number of equally spaced parallel slits. A typical grating usually contains several thousand lines per centimeter. How the light wave interfere constructively or destructively in diffraction grating is actually similar to double slit and single slit, but the difference is in the interference pattern. In diffraction gratings, the bright fringes are called the principal fringes or principal maxima. They are places where the light intensity is a maxima. That means in interference pattern due to diffraction grating, we have more than one bright spot with maximum intensity. Unlike in double slit and single slit, where there is only one bright spot with maximum intensity, which is at the center of the interference pattern. We also have bright spots called secondary maxima, where the intensity is less than the intensity of the principal maxima. So in the case of diffraction grating, we can only locate the position of the principal fringes or principal maxima. In order to determine or to locate the position of these principal fringes, we're going to apply this particular equation. So once again, m is the order number, lambda is the wavelength of light, d is the distance between slits, the slit separation. If the incident light contains several wavelengths, each wavelength deviates through a specific angle, but all wavelengths are focused at 0 degree, corresponding to a zeroth order maximum. As shown in the figure below, you can see the first order and second order of both wavelengths are produced at different angles. You can see that the first order for 700 nanometer wavelength is produced farther compared to the first order of the 400 nanometer wavelength. Example 5. A mixture of violet light and red light falls on a grating that contains this number of lines in every 1 centimeter. For each wavelength, find the angle that locates the first order maximum. What we are going to do first is we are going to convert this number of lines per centimeter, number of lines in every 1 meter. So from here, we convert this to number of lines per meter. Once you convert this, then now you're ready to calculate for the slit spacing. So this is how we calculate for the slit spacing. We'll get 1 times 10 into 6 meter. Once you've calculated for the slit spacing, you're going to apply this equation. Order number is 1. This is wavelength of light. This is our slit spacing. So this will then give us the angular position of the first order maxima for violet. Same goes for red. We're going to apply the same equation. This will give you the angular position of the first order maxima for red. With that, we have finished our topic on wave optics. So thank you for listening.
Okay, so let me explain using my the slide of from the topic of the wavelength, the second topics of the wave optics. Okay, let me share the slide first. So, uh, this is the wave optics, but for the diffraction part. Okay, as I said to you earlier, this is where we obtain, yeah, we try to learn the optics in the diffractions. Before this, we learned about interference. Okay, so this is all about single slit. But before that, okay, we need to know, at least we need to describe the interference in the thin films. Okay, so what is thin films? The thin film is a layer, okay, is a layer of material ranging from fractions of nanometer to several micrometers. Is very, very nipis. Okay, in terms of meters, is from the nanometers to micrometers. Okay, the range of the thickness is from nano to micrometers. Okay, nano is 10 power of -9 and micrometer is 10 power of -6. Okay, so this is the range of the thickness. So the constructive destructive interference of light wave is also the reason why thin films such as soap bubble, okay, this is soap bubble, show colorful patterns. So you can see here at the soap bubble, you can see a lot of color. Okay, you can see like a rainbow color at the soap bubble. Okay, this is known as the thin film interference. Okay, because it is the interference of light with reflecting off the top surface of a film. Okay, why it happen? Because of the interference of light with reflecting. This is the word reflecting off the top surface of the thin film with the wave reflecting from the bottom surface of the thin film. Ada a few surface dekat thin films. So it happens that the interference occurs from the top surface and also the bottom surface of the thin film. So the effect is present only if the thickness of the film is on the order of the wavelength of the light. Okay, so in here, there are some surface A and also surface B. You have surface A and you have surface B. Okay, from air, this is also this is the thickness. Okay, the thickness of the thin film, and this is also air. So when monochromatic light strikes the film, reflection occurs at the top surface and produce the light wave represented by ray 1. Okay, so this is a normal one. And then berlaku reflection. Refraction also occurs and some light enters the film. Okay, remember, okay, before this we learned about the behavior of the light. Okay, especially when it encounters a different medium. Okay, so some light will be reflected and some light will be refracted, akan terbias dan terpantul. Terpantul is considered to be ray 1, yang terbias itu akan masuk ke dalam dan akan berlaku lagi sekali. Ia akan berlaku lagi sekali reflecting dan akan ada yang akan refract juga. Okay, so part of this light reflects from the bottom surface of the film, passes back up through the film, eventually re-entering the air. Thus, a second light wave represented by ray 2 also exists. So remember, okay, yang reflected tadi tu akan keluar juga, keluar balik. So akan ada dua benda kita akan tengok. One is ray number 1 and number 2 is ray number 2. Why? Because of due to the thickness of the film. Itu sebab the thickness, so menghasilkan dua layer yang macam ni. So in this path different, the two tip, okay, 2 times thickness equals 1 or a whole number of wavelength lambda n in the film. The two wave will reach the eye in phase and interfere constructively. Okay, will interfere constructively. Maksudnya mata kita dekat sini lah nanti. Mata kita nampak daripada sini. So dia akan masuk ke mata kita secara constructive. If the path different equals to half, 3.5 lambda, the two wave will be out of phase and destructive interference. Jadi kalau dia satu ataupun whole number macam integer number tadi lah, 1, 2, 3 dan sebagainya. So it will be interferent constructively. But kalau dia half, 0.5, 1.5, 2.5 dan sebagainya, it will be out of phase or destructive interference. Itu senang cerita itulah. Okay, this is some ideas on how you gonna use the lambda films. Okay, how to find the wavelength of the thin film by using the wavelength of the vacuum, right? And divide by the refractive index. Okay. So you use the refractive index. So when light travels, to determine whether the refracted rays interfere constructively or destructively, take note the following facts. Number 1, when light travels through a medium with a smaller index, okay, smaller index of refraction, contoh dia air lah. Okay, towards a medium with a larger refractive index, contoh dia water. Okay, dalam kes ni water, it undergoes 880 degree, which means 880 degree phase change is considered to be 0.5 lambda. Remember, 0.5 lambda will give you destructive interference. Okay, when light travel from a larger refractive index towards the smaller refractive index, there is no phase change, upon a reflection at the boundary. Okay. Right, so yang tadi tu dia kata kalau 180, okay, dia akan menghasilkan destructive interference. Okay, but not just get the idea on how the thin films all about. Okay, so just look at the general equations. Okay, the one that you should concentrate is just the 2t. 2t means the 2 times thickness. Okay, for the destructive, we start at m equals to 0. Okay, and for the constructive, we start at m plus half. Okay, so this is the Newton's ring. Another application, just do some background readings only, so you don't have to memorize, because in the Newton's ring contains a thin films. Okay. So don't take much attention in terms of how to calculate whatsoever. Just do some background readings only. Okay, just do on the surface reading what is the thin films all about. Okay. Okay, right now, we considered the diffraction. Okay, so this one contains calculations in your final. Right, so the definitions of the diffractions, the change in the directions and intensities of a group of wave after passing by an obstacle or through an aperture whose size. So aperture ini bermaksud slit. Uh, Obstacle, okay, maybe bermaksud halangan, okay, trouble, some, okay, as the wavelength of the wave. So this is what we call as slit. Okay, so before this, we learn about interference, the young double slit experiment using double slit. Okay, meaning that two slits at one time. Okay, two slits at one time, and the effects. Okay, in other words, the light bends from a straight line. So remember, when the light travels, it travels with the wave front. This is what we call as wave front. Wave front. Okay, so kita nampak dia seolah you can say that seolah-olah dia macam ni, macam crest dia lah, macam dia punya puncak, macam peak dia. Okay, you can see macam ni lah lebih kurang. So yang atas ni yang kita kelihatan this is yang ni. So the wave travel in a straight line. However, when it encounter a slit, okay, it will diffract. Okay, what is diffraction? Spreading out light from its initial lines of travel. Okay, spreading of light. The light will be spread. Okay, look at how it behave. Okay, if we can draw an arrow should be 90 degrees to the wave front, and so do at the after the diffraction. Okay, so the arrow should be 90 degrees to the wave front. So you can see that right now, before the slit, okay, the wave travels, okay, horizontally, and afterwards, after the slit, the wave travel at every possible direction, because it will be spread out due to the slits. So in general, diffractions occurs when wave pass through small openings, obstacles, or by sharp edges. Hujung di sebelah hujung ni pun akan berlaku. Okay, light passing through narrow slit does not behave this way. Okay, a narrow slit, a light passing through a narrow slits does not behave this way, but light passing through narrow slits will diffract. Okay, if light did not spread out after passing through the slit, no interference will occur. Okay, remember, normally when the slit is bigger compared to the wavelength of the incoming wave, so there will be no interference. So nampak tak ada interference sebab apa? Because of no diffractions occur only on the same direction. Nampak direction dia, this one from left to right. Yang ni pun nampak tak ada pun yang ni. Ni tak ada. Yang ke arah sini semua tak ada. So therefore, there will be no interference occur. Diffractions occur dekat tempat tu, but it's not enough to get the interference. So look at figure B, the light from the two slits overlaps as it spread out. Okay, it spread out from the slit number 1 and slit number 2, and therefore it becomes interfere with each other, combined to get the bright and dark fringes. So diffraction by a single slit. So in this part, we want to highlight on the how can we get the diffraction by a single slit. Okay, interference, we know double slit. So for single slit, it's also considered to be diffraction. Okay, diffraction by the double slit will lead to the interference, but the diffraction by a single slit, hanya ada satu slit saja, so we call that as diffraction. So it's the bending of wave or spreading of light that occurs when a wave passes through a single narrow opening. Okay, when the monochromatic, this is the rules for the diffraction. Okay, the light must be monochromatic and of course coherent. Okay, what is monochromatic comes from the same source. And how about coherent are in phase. Light falls upon a small single stick, it will produce a pattern of bright and dark fringes. Yes, okay, for the diffraction of a single slit, it still gives you bright and dark fringe. Okay, so both the interference and diffraction will give you bright and dark fringe. The analysis of the resulting diffraction pattern from a single is quite similar to the double slit, but you can see the difference afterwards. Okay, so from a single slit, okay, you can see that there are some dark and bright fringe. I'm not sure whether we have, but in the video, have already she put the, okay, the madam put the picture of the dark and bright fringe. Okay, you can see that at the middle is quite bright, okay, and afterwards is dark, bright, like this. So bright, like this, eh? Similar is quite, okay. This one is bright. So these bright fringes for the single diffraction by a single slit, okay, and the zero here is called a central maximum. Okay, central maximum, and the light intensity at the center of the central bright fringe is considered to be m equals to 0, which is the bright fringe. Okay, so it's equivalent to bright fringe. But for the first maximum, okay, first maximum, or we call that as a destructive interference. Okay, so the decrease to a minimum intensity that equivalent to 0, the angle is considered to be sine theta equivalent to m lambda over a, where m is the order number, lambda is the wavelength, while a is the width of the slit. Width of the slit, lebar slit itu. Okay, width of the slits, and of course, the dark fringe. Okay, remember the dark fringe start at m equals to 1, and followed by 2, 3, and so on. -1, -2, and -3. So meaning that if you look carefully, the destructive interference, okay, before this in the interference of the double slit, okay, the destructive start at 0.5, 1.5, and so on. But for this part, okay, for the diffraction or the destructive interference start at 1, 2, 3, and so on. -1, -2, -3, and so on. So that will be the main difference between the diffraction and the interference of the double slit experiment. Okay. So the general equation for the destructive interference gives the value of theta, for which the pattern has a 0 intensity. So therefore, in this case, we can also use y equals to L tangent theta, while L is the distance between the slit and the screen. Okay, y is the positions, okay, the linear positions from the central maximum. Remember, the central maximum has a width of from m equals to 1, which is here. Okay, so y1 and also y2. So that is the width of the central maximum. So right, well, that's why you can say that between each pair of dark fringes, there is a smaller intensity maxima due to constructive interference. Okay, so the maxima is for bright spot, where the minima is for dark spot. Okay, so this is how the questions, examples, light passes through a slit, okay, a slit meaning that a single slit, and shines on a flat screen that is located L equals to 0.4 meters away. So that will be L. The wavelength of the light is the lambda. This is lambda. 410 nanometers. The distance between the midpoint which is the here. This is the midpoint. You know this, all of this, okay, everything is the central maximum. So half of the, from midpoint to the first dot is considered to be half of the central maximum y. Okay, um, is y. Determine the width 2y of the central bright fringe when the width of the slit is a equals to 5 times 10 power of negative 6 meters, and AB 2.5 10 power of negative 6 meters. So how we going to do? So use the first dark fringe in order to get the theta. We want to find the first theta. So first dark fringe is m equals to 1. Remember to put m equals to 1. Lambda is 410 nano, 10 power of negative 9. Okay, with a 10 power of negative 6, and then we get 4.7 theta. And then using the tangent theta equals to y over L, or y equals to L tangent theta, then we can find y equals to 0.03288 meters. Then that is y, and we want to find 2y. The 2y now 2 times the multiply here, then we get 0.066 meters. And for part B, we just okay, uh, replace A from 5 times 10 power of negative 6 to 2.5 10 power of negative 6. And then we get 2y equals to 0.13 meters. You can try on your own, okay? This is also how you're going to calculate the y of the central maximum. But that this one, they want to find in terms of degrees. Degrees mean you have to calculate what is 49 and time, and this will give you 98 degrees from this calculation. Okay, from this calculation using the wavelength. Okay, the true slit. This is A. Okay, remember, sine theta equals to m lambda over A. Okay, m lambda over A. This is the width of the slits, wavelength, and order. Okay, so in this order, we use m equals to 1. Okay, m equals to 1. And then we get 49 degree. But for both degrees, so we need to calculate both, because the slit is, at first, this is the whole thing from x, and another x at the bottom is considered to be the y of the central maximum. For interference, benda ni tak ada central maximum. Okay, benda ni ada, hanya kita calculate directly daripada m equals to 0 sahaja. Okay, but right now we need to calculate in terms of degrees and also in terms of centimeters. Okay, so this is where you calculate in terms of centimeters. And last but not least, the diffraction grating. Okay, the diffraction grating is an optical device used to learn the different wavelength or colors contained in a beam of light. Okay, so nampak diffraction grating is an applications optical device used to learn the different wavelength. It consists of large number of equal space, and typical grating contains several thousand lines. Okay, so nampak the incoming light, there are few slits here, and then we'll give you a couple of central zeroth law maximum, first order maximum, and also when m equals to 1 and m equals to negative 1. The equation is like this, but for bright fringe. Okay, so you need to use this equation in order to calculate all those things that related to the central, the diffraction grating. So it's quite simple. So we may want to calculate this one, right? So we can try this on our own, but try to do it on your own. Try to memorize the equations. Okay, at least first check the equation with the appendix. Does this equation involve or to be in the appendix or not? And then if the equation doesn't include in your appendix, then you need to memorize. Okay, so I think that's all for This week,